So as I said, this is going to be a practical talk on practical code, and it's going to be sort of a description of my journey, the journey of a middle-aged programmer through type erasure and C++. So a quick outline, I'm going to talk about what is type erasure. Who here knows what type erasure is? Okay, so not everybody. And who here knows how it works? That is, could you write a type erasure class? Okay, a few fewer. All right. So forgive me for the half that doesn't. I'm going to go over this very quickly. I'm going to talk very quickly about Boost Any, but the meat, the meat of the talk is going to be a demonstration of a configuration system that I wrote using type erasure, where type erasure solved a very good, very specific problem. And I'll hopefully demonstrate how that works. And then we will talk about conclude with showing what type erasure is good for and how I used it in this particular situation. So, in a nutshell, in its most simplest form, type erasure is something like this. You have a class C, and you want to inject another class instance into it. We call it injected instance into class C. And so notice there's a constructor here that takes an instance of tinject. Tinject is the type of the injected class. And it's going to put the instance somewhere magical inside class C. And then when we call invoke, we are going to invoke some behavior of the injected class. So you think, OK, big deal, Cheinan. I do this in my sleep. What you need to realize, however, is that class C is not parameterized on tinject. So I can't just put a member variable, type tinject member variable and invoke it. There has to be some magic to make this actually work, because only the constructor knows what tinject's type is. The class does not know, and neither does the invoke method. Okay, neither one of those is templatized on the injected class. So how does that work? Well, type erasure. What is going to happen is that we're going to erase the type of injected instance and store it erased in class C. And then when it comes to invoke it, we are going to be able to still do something with it, subject to some limitations, which you will see as we go along and look at the internals of class C. All right? So that's type erasure in a nutshell. Let's look at how this actually works. Here's the implementation of class C. And the basis for this working is this internal base right here, which I call C internal base cleverly. It's private, okay? So the client never sees this. It's all part of the implementation, hidden away from the client, and it has a virtual method called doIt, which is going to do something. And this internal base is then derived to a derived class, okay? And we are going to have a template, it's templated on tinjected, all right? And it derives from internal base. And we're going to have an implementation of the doIt method, which is virtual, so it's going to override the base class, which will actually deploy the injected class. Then we're going to have an instance of the injected class in the derived class. Finally, we're going to have a pointer to the base class in class C. All right, remember, this instance is only in the derived class, in the private derived class. We're going to have a pointer to the base class right here. And now you can see the magic that's going to happen. In the constructor, we're going to create a new instance of tinjected, which is going to be copied using the copy constructor. So right here, right away, limitation number 1, your class that is injected must be copyable. Normally, that is not a problem. In C++11, you can also move it potentially. But I wrote this in 2008, and move semantics didn't exist yet for C++. So we're going to create a copy of the class, and we're going to store it we're going to store it as the pointer in M internal base, which is a pointer to the base class. And then when invoke is called, we're going to call the doIt method on the base class pointer. And of course, this is C++ 101. You guys all know polymorphism, I hope. And right, the virtual method will be overridden, and we will call deploy on the injected class. I lost my laser pointer here. There it is. The deploy will be called, and the class will be deployed, and it will do its thing. And of course, because we use the internal base, there's no template. This is the magic of type erasure. The internal class right here had its type erased Internal base doesn't know what it is, but using polymorphism, we're able to still invoke the class and do something with it. So now you can see the other limitation of type erasure. The only thing we can do with this class is call deploy. If we wanted to call do something else, too bad. All right, the only way we could do that would be to change the implementation of C, which is intrusive. So here is another limitation of type erasure. You have to decide in advance what you're going to do with the class that whose type you erased. In order to do anything other that's useful, you're going to have to recreate its type, or at least give it some type in order to make it do something in C++. All right? Any questions about this stuff? Because this is the basics. All right, let's move on. Quick note about boostAny. So boostAny is a nice boost class that is an implementation of type erasure. And like its name suggests, what it does is it lets you put any type, any copyable type at the time I wrote this. Now I believe in Boost 156, you can actually move types in there. I tried this with Boost 155. I didn't quite get it to work. I need to try again and see if I can get that to work. I saw that the functionality was in there, although I couldn't get it to work. But for now, when I wrote this, the type needed to be copyable. But you can put any copyable type into a boostAny. And so in my little sample code snippet here, we put a string into the boostAny. We have another vector here that we're going to create. And then I'm going to put the vector into the boostAny. All right, so STL containers, no problem. And then we're going to put an int into the boostAny. Okay, we can put any type that's copyable into the boostAny, be it a class, be it a struct instance of a struct, be it plain old data, be it a built-in type, or be it something complicated. Now here you see the big limitation on boostAny. Like before, the API for invoking the classes that are type erased and stored in the boostAny is very limited. And in the case of boostAny, there's really not much you can do with it. All you can do with it pretty much is cast it back into another type. And in C++, that's what you have to do to make use of it. When I first read about type erasure, I read Scott Myers' article way back about the 4 aha moments in C++. You might want to look that up if you haven't seen it. It's a nice article. And the last aha moment was type erasure. And I read that and I was like, oh, this is so cool. Now I can write Python in C++, right? I don't have to worry about all this type nonsense when I don't want to. Joy, I don't need Python anymore. C++ does everything, hooray. I very quickly learned that I was wrong. And this is the reason. In order to do something, anything in C++ with data, you have to type it. That's life. And so you're going to have to always cast it back into some sort of type to do something. If you cast it into a type that is not compatible with what's in the boostAny, the anycast is going to throw an exception. All right? So you always have to cast it out. And in this case, as you can see, the code works, and it returns 5. All right? By the way, all of the code that I'm going to show you today builds on GCC 4.8, 4.9, and Clang 3.4. I've not tested it on Microsoft. And as you're going to see, it's actually not going to work on Windows because I'm using some Linux stuff. But also because of the way the framework is designed, it would be really easy to get rid of that stuff. So let's talk now about practical type erasure. And from here on, for the rest of the talk, I'm going to show you how I use type erasure in the wild for a configuration system. Before we get into the details of this, I just want to point out that type erasure has been around at least since 2001. Kevlin Henney, I think, wrote the first article way back in 2001. I believe I actually read it in one of those paper magazines that they had back then. You may remember those. And it didn't really impress me. I remember seeing it, but I didn't really get it. It was not until I read Scott Myers' C++ aha moments that I got it into my head and exactly what it is. And he shows why type erasure is so cool. However, type erasure has been around for a long time. The one application that Scott Myers points out is smart pointer deletion. And if you're like me, I've been using Boost since way, way back, since the 90s. And the reason I used Boost in the very first place was for its smart pointers. They had great smart pointers. You could do shared pointers in Boost, and that was a really nice thing way back then. And if you look very carefully, and I use smart pointers a lot, and I never noticed this until Scott Myers pointed it out to me. If you look in the smart pointer interface, one of the constructors to the smart pointers, to the shared pointers, takes a deleter, and that deleter is not a template parameter for the shared pointer itself. So it's type erasure, just you're injecting the deleter into the shared pointer, and then when it's time to delete the resource held by the shared pointer, the deleter is invoked to destroy this. So this is very useful to put non-operator new constructed resources into a shared pointer, like you could put a file handle, for example, or something like that, into the smart pointer. I didn't even know that existed, but it existed for a long time, and it used type erasure. You can see the same pattern again. We inject the deleter into the shared pointer. The shared pointer does a very specific thing with it, in this case, destroy the resource, and that's it. Another application is heterogeneous containers, where you can have a vector of boost any's. That's one of the very nice features of boost any, is that you can put it into STL containers. So it can be a value in a map, and it can be the value in a vector. So you can have a vector where element 1 contains a string, element 2 contains an int, element 3 contains another vector, and element 4 contains who knows what. This is actually not as useful as you might think, because ultimately, in order to make use of this stuff, you're going to have to get that type back out again, right? And so you're going to have one of those big if statements that if it's a string, do this, if it's an int, do that, or you're going to have to agree that the first element is always a string, the first element is always an int, et cetera. This is brittle. It's not maintainable. It's ugly. Remember way back when you first learned C++ that the powers that be warned you about using polymorphism properly so that you don't have to have the big if statement. And so if you use something like that, you're probably going to have some big if statements in your client code, which means anytime you change what's going on there, you're going to have to update your client code. Ugh. Don't do that. Another application was the any iterator, developed by Thomas Becker. And he wrote a nice article. The any iterator, like Boost Any, takes any kind of iterator, and then you can call the standard iterator functionality on it, operator star, operator plus plus, operator minus, et cetera. And so one of the nice things is you can put in a regular iterator into that, and then you can put a boost transform iterator into it, and you can do some pretty neat things. I would refer you to Thomas Becker's article about that if you're interested. And then finally, the big one that you may not have even known was using type erasure is std function in C++11, which people use and happily use and don't even know there's type erasure in there. But if you think about what it's doing, it's taking a callable of some form, and I'm going to use Scott Myers' language from his talk. I like callable, and you can put a function pointer, you can put a member to function pointer, pointer to member function in there. You can put a class with an operator function call, or you can put a lambda into std function. It doesn't care, and it's doing the same thing. It's erasing the type, okay, and it's going to then invoke it with operator function call. That's type erasure. All right, so type erasure, the point I want to make is that type erasure is not magic. You saw how it works under the covers. You saw its limitations, that the interface must be predefined. And you saw that somebody somewhere is going to have to know the type. Sure, if you want to have a bunch of boost any's and write-only data, you can throw type away and never care. But of course, you're never going to be able to do anything with this data. So if you want to ever do something, you're going to have to type it and get it back out again. Or I guess you could send it to Python. You can do polymorphism, but it's ugly. You're going to have one of those big if statements with if type is this, then do that. And again, do that very, very carefully, because you're setting yourself up for a maintenance nightmare when it comes time to change these types. Every client that is going to use this is going to have to update its code. Yuck. Whoops. So now to the practical use of type erasure, now that we've gone through the introduction. I was working in the government. Again, this is going to be my journey. So this is my journey. I was working in the government, and I was tasked with writing a configuration system. And this configuration system was part of a very large framework. All right, I mean very large. In fact, this framework had already 5 or 6 configuration systems, and I was expected to write the 7th one. And the configuration systems all look the same. You know, they all had, they were cookie cutter configuration systems. They had a get string. Is this working? I don't see it. Oh, there it is. Okay, they had a get string method, they had a get int method, they had a get bool method, and they had a get double method. And then you passed in the type of thing you were going to, that's how you control what the configuration was actually configuring, and it was ugly. I hated this because, first of all, you had to, the configuration system had to decide in advance what types it's going to handle, right? If I wanted to have a widget in my configuration system, then I need to write get widget. But wait, if I write get widget, every one of my clients now has to recompile because they have include myconfig.h, and myconfig.h's interface just changed. Blech. I'm thinking, it's 2008. You know, we have templates. We don't need this kind of nonsense anymore. So I was looking like this poor guy down here, and I was not happy, and I wanted to do something about it. So I sat down to design a configuration system, hopefully that sucked less, and did what we needed without using this horrible interface. And of course, the obvious solution is to use some sort of generic interface, right? You're going to use a template, and then the template will get you any type. But before I get into those details, let's talk about the requirements. I wrote down the requirements I had for my system, and they were pretty straightforward. I wanted to be able to get and set. I wanted to be able to read and write properties as well. And I wanted to be able to do this to multiple backends. So for example, maybe I want to get properties from the, properties is what we call it, it's a configuration system. Maybe I want to get the stuff from the ini file, maybe I want to get it from a database, maybe I want to get it from the environment. And furthermore, I wanted to define an order when I'm looking for data. So first I wanted to look in the environment, and then I wanted to look in the ini file, and then finally, if it's not there, I would look for it in the database. And that was nice because we could cache database data in the environment, say, or we could override values as well for debugging, which was very, very handy. And we would have a specified order for searching these things. But it was important that the client control this order of search and where you're going to look, okay? So the client gets to decide, hey, for this data, I'm looking at the database, period. But for this data, I'm going to look in the environment first, and then I'm going to look in the database. Or the client could decide he wants to look in the database first and then look in the environment. I'm not sure why, but it's his choice. I wanted to be able to return more than just plain old data. So since I'm going to dispense with the get bool, get int horror, I think, well, might as well be able to return more than just plain old data. After all, I'm actually talking to databases, so I can put arbitrarily complex data into this thing. And finally, I didn't want clients to have to recompile any time the types were added to the system. So for example, if get widget was added, clients who are not using widgets should not have to recompile. Obviously, if you want a widget, you have to recompile. But if you don't care, you don't care. So those are the requirements for the configuration framework. So here's the architecture that I came up with. The front end, there would be a front end and there would be a back end. The front end would be generic, and well, I didn't know that yet, but the front end would return any object by key. So you'd pass in the string, that's the key, and the client furthermore would decide which backends to use, and you would only compile those backends that you're using, and the client would also be ignorant of the implementation. So as you've probably guessed, I'm going to use type erasure in my framework, but I didn't want the client to be aware of that. I actually failed on that last requirement, but it's okay, you'll see. Well, I say that, but what can I do? The backend should be extendable, so that it should be very straightforward for somebody to come along and write a new backend that produces widgets. It also should support specified types. That is, the backend would know which types it supports. So for example, the environment backend would produce strings, but it wouldn't produce ints. Although if you wanted to, you could get ints out of it by converting your strings into ints. But of course, by its nature, it supports strings. The database, on the other hand, could return just about anything. So there was no limitation on that. However, each backend would know specifically what type it does and does not support. So that if you wanted an environment configuration system that supported ints, it would know that, and if you wanted one that did not, you would know that it would know that as well. And in fact, you could do both and choose, or you could even search them both. I'm not sure why, but you could. And so it was important that multiple backend instances be supported and that the client could deal them out as needed. So this is very straightforward C++ design, and as you can imagine, the obvious architecture for this is that the front end is going to be generic, right? We're going to have get with a template type T, get, and it's going to get that type. Set will take also a template. And then the back end is going to be your standard C++ 101 object-oriented guide that any freshman computer science major hopefully can write. Probably not, but maybe. And it's going to derive from a base class. Apologies to any freshmen sitting in the audience. It's going to derive from a base class. It's right. You're going to extend the base class by specializing. I don't need to go into this stuff, but it's going to be your straightforward generic OO design. So I was like, cool, I'll do this. And I still wasn't thinking about type erasure yet. The problem is, how do you connect these? You cannot put templates into virtual functions, not simply at least. It makes a big, ugly mess. And actually, I think you might not even be able to do it. And if you think about it, it makes complete sense. The template needs to be run and decided at compile time, whereas virtual methods, of course, are decided at runtime. It's not a pretty combination. So there was no way to forward a get with a template of type T into the backend virtual functions, all right? The backend virtual functions could not be templatized. So I had a problem of how do I connect this backend that has virtual functions to the front end, which has templates. And it will be no surprise to anybody that the answer is type erasure. Type erasure, and this is the key, I think, the key point of the talk. Type erasure is the glue that connects the object-oriented backend to the generic front end, and vice versa, the generic front end to the object-oriented backend. It's a very nice way to connect these two systems, and it is used over and over in this manner. The term I used is where the rubber meets the road, but Thomas Becker said it better. He literally said it. Type erasure is the glue between object-oriented and generic programming in his article. And so I just stole his better notation. So how do we do this? For the rest of the talk, I'm going to show you the dirty details of how this is actually done, okay? And it is not particularly complicated, but there's some tricks in there. And the real key for this is going to be using boost any to implement the type erasure. Are there any questions so far? All right. Here is the front end system for the client. It is, as promised, generic. All right. So there is a get method that is parameterized in some type name, and it takes a key, and it's going to return that type name. Very straightforward. There's a set method, which takes a key and a value of some type T, which is unknown to the front end, and it's going to set that value in the back end somewhere magically. We have add get handler, which takes a handler. So a handler is a backend. What I've been calling a backend is a handler. And I define get handlers, which are going to read, and I define set handlers, which are going to write. But in fact, handlers can do both. So some handlers are read-only, some handlers are read-write. You can make a write-only handler. I'm not sure why, but you could do it. I never had a need for that. So the handler itself knows whether it's read-only or read-write by the way it overrides the virtual functions. So if you override get, you're going to get a get handler. If you override set, you're going to get a write handler. If you override both, you'll have read-write handler. So handlers are both read and write. Whoops, sorry about that. Wrong button. Handlers are both read and write, so we're using the same pointer for both of them, all right? However, in the framework itself, we're going to distinguish between the two because we may want to use different handlers for reading than we're going to use for writing. It's up to the client. The client could obviously use the same handlers for both, but might not want to. And then I'm going to show you a bit of the implementation right here, a peek into the implementation. We're going to store the types. We're going to store a map that keys on the types of the various types that the handlers handle, okay? So the handlers will know, remember one of the requirements was that the handlers know what they handle. So we're going to query those types and put them into a map where the key will be the type, and then the value for that map is going to be all of the handlers that can handle that particular type. So for a string, we're going to have a list of these handlers, and for a int, we're going to have a different list of handlers, or maybe the same list of handlers. It depends on how the client sets it up. Notice that the get handler map is storing a value, a vector of handler pointers. That's because for reading data, we can have more than one handler. We can have more than one backend, right? Like I said, first we want to read from the environment, then we're going to read from the config file, then we're going to read from the database, or maybe we want to read from 5 databases. So there'll be a very specific order, and we're going to put them in that vector in order that they're going to be queried. For the write handlers, however, there is no vector, and that's because if you think about it, it doesn't make sense to have more than one write handler. You're going to write, and you want to know where you're going to write to. It doesn't make sense to try to write to the environment because you'll succeed, all right? And if you fail to then write to the database, you either want to write to the environment or you want to write to the database. You know where you're going to write to so that you have one handler for every type, essentially. If you want to change that handler, you're going to throw away the old handlers and you're going to use the new one. Let's look at the backend. This is the base class interface. I'm going to just quickly go over it, and then we'll put it aside. But this is your standard polymorphic base class, very, very straightforward stuff. It is going to, have a get, and notice here boost any is making an appearance. Remember, one of the requirements was that boost any, the implementation, not be visible to the client. So if we go and look at the front end, you don't see boost any here, all right? But in the back end, where the client doesn't get to see it, it is showing up. And so boost any is going to be the magic, again, that is going to connect this and allow these virtual functions to essentially be templatized. And so get is now returning a boost any, and set is going to take a key and a value, which will be a boost any. And get and set are going to get from the backends or set to the backends in some magical way that we're going to describe. And of course, in the base class, these methods are not going to do anything except throw an exception, because you should never be calling the base class methods. You should always override them. However, they are not abstract, because you might not want to override both of get and set, right? If you have a read-only handler, then you're going to only override get. Set will not be overridden, so I couldn't make it abstract. You're going to have a name, which is basically the name of the backend handler. It's just going to return a string. That's really, really handy for debugging. I found that when I had 5 databases in the backend and I queried them and I got some database error, it was very, very useful to know which of the databases gave me the error. So again, this is real code. And then finally, this is a vector of all the types. And I'm using the Loki library from Andrei Alexandrescu's book that you may have seen. This goes back to 2001, I think. It's a great book. It was a great book back then. And one of the things he did is produce type info from in the Loki in a way that can be used in STL containers, which is something I used right here. The regular type info from the compiler doesn't quite do that. Now there's a boost type index. I think it was Scott who mentioned it in his talk. I just learned about it in Scott's talk. So I'm going to try and replace this Loki with type info with type index. But my thanks to Andrei for making that library available. And so the final method here is going to return a vector of all of the types that this particular handler can handle. Because again, the backend knows what it's handling. So let's start looking at the implementations. The front end is very straightforward. All the front end does is it forwards the calls to private methods. In our framework system, the X prefix means private method. Here is where I lied about the implementation being hidden for the client. Because this call had to be, because it's templated, it had to be in the header file. And because of that, I exposed the boost any cast to the client. So the client actually is indirectly including boost any. There was nothing I could do about that. But it's not the end of the world, and unless the client goes digging into it, he won't know any better. And boost any's interface is pretty stable, so it's not going to be changing, forcing recompiles, I hope. And so all that the get does is it forwards it to the private get, which is going to also get the type ID of T. So we're sending both the key and the type ID of T, and then the private get is going to be the heart of the system, which is going to do the work. This is the glue method that does the heavy lifting and uses type erasure to connect the backend and front end. Similarly, for the set just forwards to the key and value to the private methods. That's all there's to it. So that's what the client sees. Not very much. This is the heart of the talk. Okay, I'm going to spend some time on this particular method, and this is where, like I say, the rubber meets the road. This is where it all happens. And don't be intimidated by all the code. I'd say about 80% of it is error correction code and error detection code, because again, this is real production code. By the way, in case you're worried, I did this work for the federal government. There's no copyright on any of this code. It's in the public domain. Grab it and go, all right? And the stuff I modified is, I think I used Creative Commons or some nice license like that. But this is public domain code, so I'm grateful to the taxpayers of the United States for making this code available. Your 10 to the minus 5 cents that went to this. So let's look at this. First of all, I want you to notice that, okay, we passed the key and we passed the type in, and well, okay, before we go there, the first thing we do is we check that there's actually a good key in there. If not, we just throw an exception on the spot. What we're going to do is we're going to take that type and look in the handler map to find the vector of handlers that can handle that particular type. Remember, I showed it to you earlier in the front end, and we set that up. I'll show you later how we set those up. But for now, when we have a type, we got a request, we want to get this type, and this map is going to contain a vector of handlers that can handle that particular type. If we cannot find a handler to handle that particular type, we throw an exception. Okay, so we found a handler, the vector of handlers for this thing, and we're going to grab it, all right? And that's going to be right here, all right, in the handler list. This is the list of all the handlers. And then we are going to call for each if on this list and query each handler in turn for the key. We're going to say, hey, handler number 1, do you have this key? And if it says yes, we'll get it. Now, for each if is not an STL algorithm. It's one I wrote, which is a modification of for each. And I'll show you its implementation in a second, but it's really straightforward. For each normally will take a functor, and as you may know, it returns the functor when it's done. And that's why I wanted this, because a little trick I'm going to use in this. However, for each if takes a predicate. A predicate, right, is a functor that returns a bool, and if the bool is true, it stops. So it's looking for something until it finds it, and then it stops returning it. I could have used std find, and I could have used a boost ref, but the government had rules. Oh, the government loves having rules. And the rules said no boost. So in fact, I snuck boost any in there by basically copying the code for boost any and putting it on its own into my code base. I wasn't allowed to use boost in general. And boost any is really, really nice in that respect because it's completely standalone. It doesn't require anything else from boost to go, except maybe like diversion and stuff like that. And if you really want to get rid of that, then you can. Boost any is very nice in that it has no dependencies, or very few dependencies. At least it didn't back then. So we're going to call for each if and query the handlers one by one for the key. If they have the key, they're going to return true. Otherwise, they're going to return false. So when we are done, we are going to stop iterating. Where am I? Iterating on the for each if, and we are going to get that functor back, that the query handler that we back in the query handler variable right there. All right. And what I'm doing is I'm storing the value that's returned from the handler in the functor. All right. So I'm in that way, I basically can then check, is there a value in the functor? Now, if there is no value in the functor, that means all of the handlers failed. So if that's the case, then I don't have that key. That key is not found anywhere, and I have an exception that gets thrown. But if the value was found, it's going to be in the form of a boost any, and I am going to get that value and put it into a boost any, which I'm going to then return. So this is the private method, the private get that returns a boost any, and as you recall, the front end is then going to cast this to the type that the user requested, and magic, the user now has his type, his data, and he's ready to work with it. So hopefully the user, the client, knows what type he wants, because he's going to have to do something with it, and this just works. Any questions about this part of the framework? This, like I said, this is the key. And this is the crest, too. It's all downhill from here. All right? So if you're with me so far, it's not going to get any harder. Let's look at the for each if implementation. Very straightforward. If you've ever looked at for each, this implementation, it's similar, except that if the predicate returns true, I stop. That's it. All right? And then I return the functor. Right? For each basically would be the same thing, except it wouldn't have this if statement. This is the predicate, and you'll notice some old style C++ things like inheriting from unary function, remember that? But this is going to be a predicate. It's going to take the key and store a copy of it, and it's also going to have a place for the value that will be returned, and you saw the getValue method returns that value as a boost any. All right, and then of course the heart of this callable is going to be the operator function call. I lost my thing. Well, operator function call, and it is going to basically query every handler in turn and get that key, and then if there's something that is actually in there, it's going to return true, otherwise it's going to return false. Yes, you had a question.
Couldn't have you used findIf and use a functor that has a side effect by keeping a reference to local that stores whatever you want as a value?
I'm sorry,
Yeah, you could have used findIf, and since you write your own functor for that, could have used a functor that keeps a value, a reference to a value variable that you just set while you were iterating and have a side effect on the predicate of the findIf, and you're done.
You are correct. So the question was, why didn't I use findIf and then have the functor like this that has a side effect with a reference to the variable that I want, and then findIf would have done the job. You're right. I think to get that done, I would need to use boostRef. Now in C++11, I believe we can do that, but back then I didn't have a way to get that reference in there. And so furthermore, for each, did this, and theoretically, this is in my ideal C++ mind, findIf should not be called, right? The algorithm should not be called with functors that have side effects. So even though I would have gotten away with it, no question about it, I was being a good boy, and I didn't do it that way. And whereas for each does allow predicates with functors with side effects, right? That's the whole point of for each, as far as I'm concerned. And so I did it that way. But you're right. You could have used boostRef, and you could have used findIf, and I wasn't allowed to use boostRef, so I couldn't use boostRef. But you could certainly do it that way. And again, today, if I were writing it today, where we actually have the reference wrapper in the standard, yeah, that's totally doable. Any other questions? Good question. Thank you. All right. So yeah, this is pretty straightforward stuff. Do you guys see my laser pointer? Oh, there it is. There it is. I found it again. All right. I keep losing it. So we return the value we return true if there's a value. We return false if there's no value. Right away, does anybody see the limitation with this system? There is a big limitation here. Anybody see it?
Exceptions?
You mean in the back end?
Yeah.
You're right. We do not handle exceptions in the back end. But basically what would happen is the exception would get propagated, and we would get the exception report. So the back end, I'm sorry, the question was, what about exceptions? But that is not really a problem. If an exception is thrown, the way this configuration system was working, I wanted to know about it, and I wanted it to stop dead and handle it. And so, for example, the database was a very complicated system, and we threw exceptions when things broke purposely. So that's not what I'm thinking about. Anybody else? I'm sorry? Oh, I didn't even think about it. So the question was, it's not thread safe. I have no idea. Didn't even think about the thread safety. That was not an issue for us. Generally, I don't know that configuration systems need to be thread safe because, you saw the requirements in there, and speed and thread safety are not, fortunately, not requirements usually for configuration systems, right? You read the stuff in the beginning, and then you can pass it out to the threads. So that was not something we worried about. We actually did have not just threads, but we had distributed computing going on in the system. But we just pre-read everything and handled it later. No, yeah.
Making an assumption that underscore value is a string.
I am not. Where am I making that assumption? So I'm sorry, the question was, I am making an assumption that m underscore value is a string. I disagree. I'm sorry, where I'm calling what? No, I'm calling, right, but empty is a method of boost any that tells me if there's nothing in the boost any. All right, so let me see here. When you construct, notice that I'm not explicitly constructing the boost any, okay? So when you construct a boost any with its default constructor, which I'm doing, you're going to get a boost any that will set empty to true, all right? And then only if I assign something into it am I going to actually not have boost empty call, all right? So no, I don't have to put a string in there, all right? Colin, I think you said you were on the right track?
That's effectively your type erasure. Calling, it can be anything that implements empty.
No. Empty is being called on the boost any itself, not on the contents of the boost any, all right? So the empty is just being called on the boost any. So I can put an int in there, and that's fine. I think somebody else might have, I thought I heard it. But empty is the weakness, all right? In a configuration system, sometimes you want to distinguish between a key not being there and a key having an empty, explicitly empty value. And that's the weakness of the system here. You can't do that. The only way I have to show that a key is not present is to produce an empty value. And if the configuration value is actually empty, it's not going to find it. That is a weakness here. In this system, I actually solved that by creating an empty class. So I called it Cempty trait or something like that. And I used that as a marker for an empty value. But that made my code ugly because now I had to do, if it's empty, then do this, otherwise do that. It's not a pretty solution. And so I didn't show it over here. I'm not very happy with that solution. But that is the one way to do it. Also, for the question on the exception that you asked, I want to point out in the real interface, I also had in the front-end interface, I had a method which caught the exception, the boost any cast exception. And if it was caught, it returned the default value. So you could pass in the default value and then catch the exception and then return. So it's called get with default, I think. Since we're talking about tricks that I used in the system, there's one more trick that, and if you think about it, it's a weakness in the template system, and that is if you want to return C strings, okay? You cannot return C strings as template arguments very well because the argument depends on the length of the string, and it's not pretty. It doesn't work. What I did was I specialized get to use C strings explicitly, and then if you started C string and I looked for its type, if it was that type, then I would call that specialization and handle the C string. Again, just a bit of ugliness that I'm not showing you in the presentation here. All right. Any other questions? So let's continue. Here is the setter. This is the private set method. It's very similar to the get, so I won't belabor it. But again, this is mostly error checking. We check that there's a key. We throw if there isn't. We get the type. We get the handler for that type. It's a map. But this time, we don't even have a vector. We just have one. So it's much simpler. If we can't handle that type, we throw an exception. We can't handle that type. And then we get the type. And we call set on it on the back end. Remember, the base class had the set method that took a key and a boost any value. Notice that the signature here takes a boost any, but we automatically converted. So the front end had the set which took the template, and the template gets automatically assigned into the boost any, no casting required. So the boost any just goes in there, it just works. Only when we're going the other direction do we have to cast. And so we call set on the back end, and all is well. All right? This is straightforward and simple because we don't have that vector of handlers. We have one, and so we don't have to do all of the for each if stuff. This is the add get handler implementation. So this is where I'm adding a new handler. It's a bit tricky, but not too bad. Really what we're doing is we're taking the client wants to add a new handler, so we get the pointer to it. And of course, this is all object-oriented stuff, so we're going to get a pointer to the base class. And the handler is going to be instantiated by the client. He's going to call new, instantiate it, pass it in through the base class, and into this method. We're going to get, remember we had a method in the handler that gave us all of the handle types in a vector of type infos. So we're going to walk that vector of type infos. Here's a bit of C++11 that I put in there because when I wrote this code, I changed the names from the original. It had these original specific names. And when I did that, I couldn't be bothered to figure out what the type of that iterator was and the loop, so I just used auto. And we walk all of the types that are being handled, and we insert each one into the appropriate vector, basically. So we get the vector of handlers that that type can support, and we stick that one into the back of it. So the client's responsibility is to add the handlers in order, and as long as the client does that, that order will be maintained, and then the client can search them in order, and the client stays happy. The set handler is much, much simpler, of course. We only have one handler potentially, so we look up the types in the map. Oh, this is wrong. I'm sorry. I'm using the old slide here. We're actually going to loop through all of the types that it handles, and then for each type, we're going to put it in. So my apologies for this slide being incorrect. I'm pretty sure in the actual code it's correct. I hope so. If not, I will correct that this week. So we saw the base class again. I'm not going to go through this again. What I want to do in the rest of my time is show you some instances of backend handlers. Okay, I'm going to show you exactly what we did. We're going to start simple, and we're going to get more complicated. This is, again, the base class. We have virtual get, we have virtual set, we have name, which I'm not going to show you, and we have the get handle types, which is very straightforward. So the simplest handler that you can have is a simple, what I call a memory handler. I call it the memory handler. And what it does is it's going to take exactly one type, all right, t value, whatever that might be, and it's going to store it in a map. And there'll be keys, and it will store in the map. So this can be ints or strings or something like that, whatever you want it to be. And so it stores only exactly one type, and so the create type vector is going to, the get handle type is going to be a vector with one value, and that's going to be the t value. Create type vector is a helper function that I wrote, which converts all of the template arguments into a vector of type infos for those template arguments. I did this the old-fashioned way in 2008 by having, the one for one vector, for one template argument, one for 2, one for 3, one for 4, all the way up to 10, 15, or 20, whatever, until I got sick of typing those things in, copying and pasting them. Today, you'd use variadic templates. It would be much simpler, right? I think Boost MPL could probably do this cleanly too, but I couldn't use it. So let's look at the get and set. All right, let's look at, I lost my guy again. There he is. Get is very straightforward. We pass in a key. We have a boost any that we're going to initialize, and we're going to look it up in the map. And if it's there, we're going to put it into value, and we're going to return it to the client, right? And whatever's in the map, whatever t value is, automatically assigns into value right here, no problems. And we return value to the client, who's going to cast it back to the type that they requested. Similarly, set, very, very straightforward. We pass in the key, the boost any value. We put into the map. Can't get much simpler, all right? Here's a real handler that I actually used, although it is modified. I modified it because in our framework, we actually had a framework for handling the environment. And instead of using the specific code to that framework, I wrote this to be Linux generic. I'm sorry, I don't have access to a Windows machine to test this on Windows. I don't know how to do that off the top of my head in Windows, but I'm using getenv, essentially. So get now takes the value. It assumes it's a string, and as you can see, create type vector only has one type. It's strings. So this is all that this environment handler handles. We convert the string to a C string, and we call getenv on it, which is the system function call on Linux that gets something from the environment. If we get a value out of it, we're going to construct an std string, and we're going to return it in the boost any. This std string gets put into the boost any, and we return. Again, very straightforward. Set is similarly straightforward. We set up the key equals value using the value that we have from a C string. We're casting the C string we're casting the value, which is a boost any, to an std string. So we're assuming that this is an std string, but it must be an std string because we only handle std strings here, all right? So this is why the handler needs to know its type. We will never get an int here. If we called an int on this thing, this guy wouldn't be registered as a handler for ints, and we would never be able to set it in the first place, all right? So if you tried to write an int to this guy, an exception would get thrown. And so we put that, we take that string, we put in the key equals value format, we convert to a C string, which is what putend requires, make sure that it actually worked, throw if it didn't, I'm omitting this code, and that's set. So when set is done, the new key value pair is in the environment. All right? Again, very straightforward. I have just enough time to show you a more complicated example, but if there are any questions, let me take them now, because I'd rather take questions than go over the example. So please.
Earlier you mentioned how smart pointers, especially shared pointers, they use type erasure to erase the deleter. But I guess
when they have a customized deleter, not
correct.
in the default form.
Correct, but it seems like unique pointer doesn't do the same thing. It doesn't have a type erase deleter. Why is that?
I think it does, actually.
It provides a default deleter.
No.
It's a default template parameter, but it doesn't type erase it. So I don't know why that decision.
I can answer that.
Okay, please.
Unique pointer tends to be more, type erasure requires an additional pointer, and unique pointer wants to be the same size as a regular pointer, and therefore there's no type erasure. I proposed to have a special unique pointer with a type erase deleter, and that was voted down by the committee.
Well, there you have it. So thank you. Thank you for the much better answer than I would have given.
I've been there.
So, yeah, but obviously nothing stops you from implementing a unique pointer with a type erased deleter. It would just be larger. Any other questions?
Hi. I thought at the beginning you were saying the benefit of this is you could save T-widget, but does this mean you need to implement a backend for T-widget every time? So you implement your class, you want to serialize it, and you need to write a backend because they're specific.
Yes. So in order to have a T-widget backend, you're going to have to implement the T-widget backend because you're going to have to store your T-widget somewhere, right? Be it in the database. This is a configuration system after all. You could create them on the fly from your keys if you wanted to. So there's nothing stopping you from having a backend that's the factory function that takes the key and returns a T-widget. That, in fact, we did something like that. But yes, you're going to have a specific backend for the T-widget. You can't have a generic backend that just does everything. The backends must know the types that they can produce, and that's a requirement for the system.
Okay, thank you.
Anything else? All right, I think I got a bit of time, so let me go over some of the more complicated backends. Okay, thank you. This will be perfect. I'm just going to go over this quickly. For the code, for the talk here, I created this JSON. We didn't actually use JSON back in the framework, and it's going to have, again, there we go. It's going to have some strings, last name and first name of strings. It's going to have an int. It's going to have a map of strings to strings. So address is a map, all right? And it's going to have phone number, which is a vector. So this is more to demonstrate the types in a more complex system. So we're going to have this JSON schema, which is going to have two strings, an int, a map, and a vector of structs. And these structs are going to have two strings in them, okay? Maybe you wouldn't do this in real life, but again, this is an illustrative example. So I want to store this JSON in a backend, and I want to be able to query it. So I want to be able to say, give me the first name, and I'm going to get Homer, or give me the age, I'm going to get 38, or give me the address, and I'm going to get the map that is going to be address. Okay? So this is going to be a backend that's actually going to return multiple types. It's going to return the strings, it's going to return the ints, it's going to return a map of strings to string, and it's going to return a vector of phone numbers, where phone number is a struct. And here is where the ugliness begins, all right? I'm not going to go into this in detail, but so this is JSON Spirit code. So again, if you're going to want to compile my code, you're going to need to download JSON Spirit. And JSON Spirit, as you can guess, uses Spirit, so that's Boost, so you're going to need Boost as well. The instructions are in the README, but hopefully you shouldn't have much trouble with that. But JSON Spirit basically needs you to tell what the type is when you get the value, all right? So JSON Spirit is going to automatically load this map. So now notice I'm using Boost Any in the backend itself, all right? And the keys are going to be first name, last name, etc., address. And then the values are going to be a string, an int, a map, all right? So address is going to be in map, and I'm going to put that into Boost Any. Or the vector of phone numbers where phone number was a struct that had 2 strings in it, all right? So mValues is going to be this map based on the key that's going to contain all these Boost Any's. When the client wants to get the appropriate value, he's going to supply a key. So if the client says, give me the address, he passes an address, and he's going to get a map of strings to strings, all right? And that map is what the client will get back, and so the client better be expecting it, or he's going to get a big surprise exception, all right? Again, you see the weakness of the system here. You're going to have to predetermine the schema of the JSON. If you want to change the schema of the JSON, you're going to have to redo the client. I'm sorry, redo the backend. Okay, the backend has a schema built into it, and I don't see any way to get around that. However, what's really cool about this is the client doesn't have to care about the backend. So yes, there's a lot of ugliness here, but this ugliness is hidden away from the client, and that's a nice feature of the system and a nice feature of the type erasure. The type erasure allows you to hide the sausage making under the rug, to overuse metaphors, and concentrate on what the client wants, which is, I have a key, give me a value. I don't care how you did that, just give it to me, and spare me your travails of ugliness and, oh, you poor backend implementer. I don't want to hear about it. All right, so this gets pretty ugly, and of course this was a simple example, but if I wanted to add something to this, I would have to change the backend. However, notice if I wanted to add something to this and I didn't want to use it in the client really doesn't care. The client still works, although the client would have to recompile. Finally, if you think this was ugly, here's real life ugliness, okay? This is actual code from the system that I didn't change the names, so we have all the ugly names and stuff like that, but that's not the ugliness. This is a real life backend that went to a database to get an int. Now, this database, there were actually, I think, 4 databases, maybe 5, and the int was in a bunch of tables that were joined together. Don't ask me. It was a mess. You constructed this SQL query, and I didn't work on this side of things. I just put the query in there, and they got it. And so now you can see that we have private methods to connect to the database. This is the one that actually got the int. The build ID was the int that we wanted to get, and the result. And we had a method that constructed a SQL query to do this. And notice this. This is the original name of the property system, of the configuration system. We have a configuration system in the backend of the configuration system. And the reason for that was that we got all the database data information, how to connect to the database, from the environment. So got nested configuration systems. This works perfectly well, all right? You can do whatever you want in the backend. Again, and the nice part is that all this ugliness is hidden from the client. The client does not know that this is going on. And this was a great improvement over the way that it was happening before, where the client would set up the database connection, the client would construct the SQL query, the client would read the environment, and then if you change the database schema or how the SQL query was put together, the poor client had to go and update all of his code every time he used this. Oh my God, what a mess. And so by doing it this way, the type erasure lets you hide all of this ugliness in the back where the client can't see it. If we want to change the SQL query, we just change it in the backend. If we want to change how the databases are connected, we just change it in the backend. The client never changes. Sure, the client would have to recompile if we change this, if he's using this particular thing, but the ugliness is hidden. And speaking of ugliness, don't look at the last line. This is code from 2008. Yes, that's an auto pointer. I was not allowed to use Boost, so I used an auto pointer I'm sorry, I had no choice. All right, so just quickly I'll mention additional applications for type erasure. You can have a heterogeneous factory. Typically a factory will have to inherit from some base class, but with type erasure, you can really return anything. This is, again, not so useful because you'll have the big if statement. And a registry is something you can do where you're going to register instances of classes through types, and you don't have to inherit from a common base class. So to conclude, type erasure is not magic. It's not going to allow you to write Python. If you want to write Python, write Python. And if you want to write C++, write C++. Somebody somewhere is going to have to cast. There's nothing you can do about it. But what type erasure really does, and I hope I showed that to you today, is that it helps you expose a clean interface to the clients and make your client's life much better, especially you saw with the database. Getting that out of the client's way was such a nice thing. And so even when your internal implementation is a mess, the client just doesn't care. And then hopefully what I showed you, that type erasure has limited applications, but one of its most useful application is to connect object-oriented and generic code together, which is what I did in configuration framework right here. So thank you, and I'll be glad to entertain any questions.